Hello, ladies and gentlemen. I hope you're as eager as I am to take a look at question number 3 in Part B of the 2015 Canadian Intermediate Contest. We're going to finish off this paper, and hopefully we'll do it in style. So question 3 has got a bit of a preamble here. Heron's formula, which is a very important formula, says that if a triangle has side lengths A, B, and C, then its area is equal to the square root of S times S minus A times S minus B times S minus C, where S is 1/2 of A plus B plus C. Heron's formula is pretty interesting. It doesn't come up a whole lot, but it's a great way to calculate the area if you don't know, for example, things like trigonometry and stuff like that. Okay. So S is typically called the semi-perimeter. Yep, this is the usual Heron's formula stuff. I should probably do a video on Heron's formula, frankly. It's kind of nifty. But that's neither here nor there right now. So, question 3A. In the diagram, triangle ABC has side lengths AB is 20, BC is 99, and AC is 101. If H is the perpendicular from A to BC, determine the value of H. Okay. Well, I see a right angle triangle there, so there's actually probably two ways we could do this. I see we've got H as one of the legs of a right angle triangle, 99 is the other, and 101 is the hypotenuse. We could just jump in with Pythagoras Theorem. 101 squared minus 99 squared, what's that going to be? 400. And then square root of that should be H, so H should be 20. If I do that in my head, I get a little confused because AB is 20 and it appears to make a triangle. So we could do that, and I could double check my arithmetic, because sometimes my noggin just doesn't do all the math in its head the right way. Or what we could do is probably the intended way is to take Heron's formula for a ride. So Heron's formula allows us to compute the area of this triangle. We do have all the outer side lengths for the triangle. And then we have not a base, but we do have a height, h. I wonder what we can do here. Yeah, BC is 99, so you can't just jump into Pythagoras. Wow, I wonder how many people did that. Just assumed you could do 99. Yeah, you have to use Heron's formula. Okay. Jumped the gun a bit there. Glad I caught that. Kind of looks silly, but whatever. Let's keep going. So the base is 99. The height is h. So our area should be 1/2 base times height. And that's 1/2 99 times h. Okay. And that works out nicely. So that's a way to get the area, and it's got an h in it. If I knew the area, I could just solve for h. Now, fortunately, I have all the sides for my triangle. 99, I know the 101 looks shorter than the 99, but it's my picture. Well, we have all the sides here. So we can use Heron's formula. Let's compute the semi-perimeter. So we add all them up. It's just the average of the side lengths. Unfortunately, the 99 plus 101 gives us 200, so 220. We'll get 110. So area, and this is one that we'll actually get an actual answer for, we get 101. Sorry, 110. 110 minus, geez, that just looks messy. 110 minus 20, 110 minus 99, and 110 minus 101. All right, let's get cracking. 110, we can't do anything about that right now. 110 minus 20, that's going to be 90. 110 minus 99, that's going to be 11. And 110 minus 101, that's going to be 9. Okay. Well, I could calculate this all out with my calculator, or I could realize 110 is 11 times 10. 90 is 9 times 10. We got 11, and we got a 9. So really, this is the square root of, we've got two 9s, so 9 squared, times 10 squared, times 11 squared. The square root and the square signs cancel each other out, and we're just going to be left with 9 times 10 times 11, or 99 with a 0 on the end, so 990. Okay. So we got 990. And we know that that's going to be 1/2 99 times h. So 990 is 1/2 99 times h. And if we multiply by 2 on both sides, we'll get 1980 over here is 99h. Divide by 99 on both sides, and we'll get 20 is equal to h. So the number that I predicted by foolishly doing Pythagoras' theorem, which I shouldn't have, and again, I apologize, I was doing that way too quickly, I still get a 20 here. And I think that's because 20, 99, and 101 actually are, it's a Pythagorean triple. So AB happens to be a perpendicular. It's not shown in the diagram properly, and it's very confusing. So I wonder if they knew that when they set it up, or they just picked these numbers because Heron's formula gave you a nice answer. Questions, 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 but nothing we need to handle. We have h, and we have it through the math. Like, it actually works out. And even our irrational, going too quickly Pythagoras' theorem backs up that 101, 99, and 20 will form a height there, because it's a right angle triangle. Anyway, enough about A. We got our H. Our H is 20 there. Now we're on to B. In the diagram, trapezoid PQRS has PS parallel to QR. Great. And PQ is 7. QR is 40, RS is 15, and PS is 20. If x is the distance between the parallel sides, or the height, determine the value of x. Okay. Okay. What can we do here? Well, I'm always mindful of the fact that we are given Heron's formula, and I'm betting that they didn't give us that just to do A part. They probably are going to have us use it for B and C. So with a trapezoid, I'm thinking, where can I get triangles? Where can I get triangles? Well, actually, I don't think... I'm thinking of dropping perpendiculars from B and S. Those will have height x. That'll be fine. And we'll get right angled triangles. And maybe that's enough to calculate? Let's see. So we had... which way was it? Was it clockwise? Usually they do clockwise. Nope, counterclockwise. B, Q, R, and S. I know this one's 20, 15, 40, and 7. I'm going to drop perpendiculars from P and S to QR, and call the points A and B. Okay, so let's do orange. Perpendicular and a perpendicular, and these are going to have X as their length, which I'll make a note of in a moment, and we've got A and B. So PA equals SB is equal to X, but we have more. PSBA is a rectangle. Right, we also have right angles here because they're parallel. P and S is parallel to Q and R. So AB is the same as P and S, which is 20. So we've got leftover amount QA plus BR is going to be 40 minus this 20 in here. So I'm going to say let QA equal Y. Then BR is 40 minus 20 minus Y, or 20 minus Y. Okay. we have two right triangles. And sadly, right now, I'm not seeing anywhere to do Pythagoras. Or sorry, not Pythagoras, to use Heron's formula. I'm thinking about using Pythagoras, which did not turn out well for me last time. I almost did the question horribly wrong. So we got two right triangles, and that would be PAQ and SBR. So let's see what happens if we go by Pythagoras. We have x squared plus y squared is equal to 7 squared. And x squared, this time it's going to be plus 20 minus y squared, is 15 squared. Okay, well, I can expand. I can say the 7 squared is 49. I can say this guy here is 225. And I can expand this out. If I know the binomial theorem, that's great. Or I can use FOIL, either way. So got x squared and 20 squared is 400. Saw that last time. Minus 2 times 20 times y, so that's 40 times y, plus y squared. That's 225. And I notice the first equation has an x and a y, and the second equation has an x squared and a y squared. I think I'm going to be able to get y using the quadratic formula, and then from there I should be able to solve for x, which is what they want. So let's take that last equation, 225, and we're going to group the x and the y together. We also have 400, and we've got minus 40y. Right? Oh, it's not even going to be quadratic, it's just going to be an actual y value. X plus y, or x squared plus y squared, we know it's 49. So we have 40 there, and minus 40y. So 449 minus 40y, that's great. Was it? I thought it was, No, okay, it really was, so we can get the x squared and the y squared together. Alright. My mistake. I thought there might be another y squared in there, but it wasn't, so that's two goofs on my part today. We can bring the 449 over to the other side, or we can bring the 40, I'm going to bring the 40y over here, make everything positive. We're going to get 449 minus 225, which is 400 minus 200 is 2, and then 49 minus 25 is, it's going to end in a 4, it will be 24. 224. Let me just double check that on a calculator so I don't make any more mistakes today. Yeah, okay, so that worked out great. So, both of these have a factor of 4. Oh, I think they have a factor of 8. Yeah, they both have a factor of 8, so we get 5y is 28. Or y is 28 over 5. Alright. So x, we know x squared plus y squared is 49. Great. And now we know y squared, so x squared is 49 minus 28 over 5 squared. I'm betting x will be something over 5. Just calling it now. So we get 49, and then 28 squared is, 784. Yes, calculator confirms that. And then we do 49 multiplied by 25 because I want a common denominator. I get 1225 minus 784 all over 25. And minus 784. So x squared is equal to 441 over 25. 441 is a square, so x is going to be 21 over 5. Okay. Just double checking some things on my calculator. And I wish my calculator's buttons weren't so sticky, or I'd already be done this calculation. Okay, there we go. Oh, it's a 3, 4, 5 triangle. 21, 28, and 35. Nifty. All right. What else can we... Oh, so we have our x, and that's all we needed. Right? That's what the question asked for. Determine the value of x. Alright. A little sad that we didn't use Heron's formula in there, but maybe this is just a general triangle question. So I'm going to write it again, but put a box around it. Alright. And now C part. The last part, this should be a challenging sort of theory-ish question. Let's see what we've got. The triangle with side lengths 3, 4, and 5 has the following properties. It's a good triangle, good right angle triangle. Its side lengths are integers, okay. The lengths of its two shortest sides differ by 1. The length of its longest side and the semi-perimeter differ by 1. Ooh. The area is an integer, and the perimeter is less than 200. Determine all triangles that have these 5 properties. Oh, okay. Well, if its perimeter is less than 200, and the semi-perimeter is just the perimeter divided by 2, that makes the semi-perimeter S less than 100. That's something to note. Okay. I'm just going to say, let A, B, C. I'm going to order them, actually. Talk about the shortest sides. Because they were talking about shortest and longest, so it might as well make sense to single them out. So let those be the side lengths. And S is equal to A plus B plus C over 2 equals, and that's the semi-perimeter. Okay. So we know A and B differ by 1. That was one of the properties. So we want A, B, and C to all be integers. That's not something we can guarantee right now, but we can say A and B differ by 1. So let's just get B in terms of A. Okay, maybe later on we'll need A in terms of B, but I think right now this is a safe bet. Maybe we'll get everything in terms of A, and then just be able to solve for integer values of A. That's possible. So we've got our B, and if we needed it, the only formula we've got right now is talking about the semi-perimeter. So now it's A plus 1 plus C over 2. That doesn't really help us right now. But we also know the semi-perimeter and C differ by 1. Is there a way to use that? Is there a way even to tell which one's bigger? Can I say the semi-perimeter is C plus 1, or might it be C minus 1? Does the semi-perimeter have to be bigger than the longest side length? Well, on our example, we've got 3, 4, 5, which has a semi-perimeter. It's got a perimeter of 12. Divided by 2, that's 6, so that's bigger. So I think the semi-perimeter will always be bigger than C. Oh, okay, triangle inequality, that might do it. Yeah, okay. So in a triangle, we have what's called the triangle inequality. I think this will work. In order to make a triangle, A and B have to be longer than C itself, otherwise they would lie flat against it. So A plus B is always greater than C. So the semi-perimeter, which is A plus B plus C over 2, is always greater than C in place of this AB plus C over 2. So that's 2C over 2. So S is greater than C. That tells me that S has got to be C plus 1. Alright. So, now I know that C plus 1 is A plus 1 plus C all over 2. Or I could say 2C plus 2 is 2A plus 1 plus C. I can bring one of those C's over. And I'm left with C plus 2 is 2A plus 1. So, C is now 2A minus 1. And that does work on the 3, 4, 5 triangle. 2 times 3, the shortest angle, or shortest side, minus 1 is 5. That's C. Okay. So we do have B, C, and we can actually even get, so our semi-perimeter, S is C plus 1. I don't know if we'll need this, but it's 2A minus 1 plus 1. Semi-perimeter is 2 times A. I want the area to be an integer. I think this is the last property, integer, other than having A, B, and C be integers, and those will be integers if A is an integer. So actually, I'm going to make a note of that first. We have A, B, and C in terms of A. So if A is an integer, we see it follows that you add 1 to an integer to get B, you're going to get an integer. So if A is an integer, we see it follows that B and C will be integers. Okay, so B and C will be integers too. Alright, so now we need area to be an integer. I think that was the last condition. Let's just do a rundown. Side lengths are integers, so we just need A to be an integer. Great. Lengths of the 2 shortest sides differ by 1. We've got that. Length of the longest side and semi-perimeter differ by 1. We've got that. Area is an integer. Perimeter less than 200. That'll probably... So we should probably make a note of the perimeter first. Okay. So again, we'll have to delay this comment. We'll probably do it on the next page. But area of being an integer, we have a formula for the area in terms of the semi-perimeter and everything. I'm going to make a note here, by the way. This is triangle inequality. You should probably mention it because it's a written solution, so you should probably mention that somewhere. Okay, perimeter. That's A plus B plus C. That's less than 200. But A is A. Cute. B is A plus 1, and C is 2A minus 1. Less than 200. So the 1's cancel out. We're left with 4A is less than 200, or A is going to be less than 50. Useful to know. Okay, so A is less than 50. That's a good piece of information. Now we've used everything except area as an integer. So area, by Heron's formula, is square root of S, S minus A, S minus B, and S minus C. But I know that S is 2A. So this is 2A minus A. 2A minus, well, what was B? B was A plus 1. So if we're subtracting B, we get A, and then we get a minus 1. And then 2A... so the difference between those guys is going to be 1, but let's just write it out. 2A plus 1. There we go. So that's going to be 2A times an A times 2A minus A is A minus 1, so A minus 1 here, times 1. So square root A squared, A minus 1, or really we can take the A out and we'll get square root of 2A minus 1. So to be an integer, A must be an integer, and 2 times A minus 1 square rooted should be an integer. Actually, you know what, we're gonna... I worry that making the assumption that A is an integer... Well, no, that should be fine. I wish there were an undo for the erasing. So for A to be an integer, we must have square root of 2A minus 1 is an integer. So let's let it be, I don't know, K. So we can square both sides, and that's really what we're looking for. 2a minus 1 is equal to k squared. So now we're looking for values of a that when we subtract 1 and multiply by 2, we get a perfect square. Okay, and a's got to be less than 50. It said less, right? Not less than or equal to. Perimeters, it probably doesn't matter, but perimeters less than. So we get a is less than 50. A minus 1 is less than 49. So 2 times that amount, 2 times a minus 1, is less than 49 times 2, which is 98. So k squared is 98. So what are some perfect squares that are less than 98? We've got 1, which probably won't matter because we need it to be even. 4, 9, 16, 25. All the odd ones we won't need. 36, 49, 64, and that's it, because then we get to 100. Okay. So I'll make a note, can discard the odds as 2a minus 1 is even. Okay, so now we have 4, 16, 36, or 64 to check. Well, I think they'll just give us values for a. So 4 is 2a minus 1. So 2 is a minus 1. A is going to be equal to 3, and then we get 4, 5 for B and C. Okay, that's the one we've already got. And then we have the next one is 16. 16 is 2 times a minus 1. So 8 is going to be a minus 1. So A is going to be 9, B is going to be 10, and C is going to be 2a minus 1, wasn't it? So it'll be 17. Okay. Does this give us proper area? So 2a minus 1. Yeah, it should be an area of 4 times, because square root of 16, so it'll be 4 times a, so it'll be an area of 36. I can believe that. 36. I don't think we needed to list all these out. I think they just wanted the number, in which case 4, 16, 36, and 64. There's 4 possibilities. But let's work them out. So that's going to be 18 is equal to a minus 1. So we got a is 19, b is 20, and c is 2 times a, which is 38 minus 1, so 37. And the last one, 64, is 2 times a minus 1. And we're going to get 32 is a minus 1. So a is 33, b is 34, and c is 2 times a, 66 minus 1, 65. So those should be the triangles. And if we take a look, perimeter, 33 plus 34 is 67 plus 65. That's well below the target. That's going to be 132, I think. That's well below 200. But if we did one more, we'd get 100 is equal to 2a minus 1. We'd get a is 51. And then we'd get 51 plus 52, so that's 103, plus 2 more 51s minus 1, so that's 101. And that's 204, so that'd be too big. Okay. Just some mental math there. But what was the question actually asking us for? Determine all triangles? Okay, we actually did determine all the triangles. I thought they might just be asking for the number. Oops. Gotta plug that in. So here are our triangles, but let's list them out nice and neat. So the 4 triangles satisfying these 5 properties are, we'll list them as triples, 3, 4, 5, 9, 10, 17, 19, 20, and 37, and finally 33, 34, and 65. Okay, and that's all we were asked for. We've got 4 of them. Let's just take a quick run through of what we did to see. It should usually be an involved question. If we have the time, we should double check and make sure everything worked out. Alright, so we stated some side lengths, we got ourselves a semi-perimeter, and one of the first things we looked at was said we can get b in terms of a. Great. So b is a plus 1 because they're supposed to differ by 1 and a is the shorter one. Then it took us a moment, but we said the triangle inequality means a plus b is greater than c, and so our semi-perimeter is greater than c. And since they differ by 1, the semi-perimeter has to be c plus 1. As opposed to the alternate possibility, it could have been c was bigger than s, and so s would be c minus 1. But apparently that can never happen on any triangle, and now we know why. Triangle inequality. Great. So getting back to the question, we know we were then able to solve for c in terms of a, 2a minus 1. So now we've got all our side lengths in terms of a. If a is an integer, they are integers. And that'll satisfy the first property, and we've also satisfied the next two properties. So now what's left? Perimeter needs to be less than 200. This gives us a bound of a can be no more than 50. Actually, it can't be 50 either. It's going to be no more than 49. So the last thing is area's got to be an integer. When we plug everything, we can get an expression for the area in terms of a. And we work our way down, and we get the area is an integer if square root of 2a minus 1 is an integer. So that means 2a minus 1 is going to have to be a perfect square. Thanks to the perimeter, we have a bound on a, and that gives us a bound on which possible perfect squares it can be. Going to have to be the even ones. 4, 16, 36, 64. That means 4 different areas, 4 different triangles. And we worked them all out to get our triangles there. Not a bad list. Not a bad question at all. Great way to wrap it up. Not a whole lot else to say. I liked this contest, personally. I think they get better and better each year. It's important to remember, Cimc has only been around for, I guess as of this one, 5 contests. Okay? But I like them a lot. They're good, and I have fun doing them. And hopefully you guys have fun doing them too, because I think that is of the utmost importance. I mean, say what you will about trying to place well, be school champions, bring up your school's math profile, or trying to get scholarships, or just trying to look good in general. You can put things like school champion in the Kaylee contest on your resume. I did at one point when I had nothing else to put on my resume for my very first job. I put that on, and that's like saying captain of the football team. It's essentially meaningless, but it does have you stand out a little bit. Say what you will about all those things. Those are great reasons to do contests, but above all, you should be having fun. That's why it's a contest, not nationwide math exam to induce fear into you. It's supposed to be fun. You're supposed to have fun. You're supposed to say, oh, that's a cool property, or wow, I'm really satisfied with how nicely and neatly I did that. That's a good solution that I came up with. And I compare it to the answers they posted, and their answer is nearly as nice as my elegant solution. It's supposed to be fun, it's supposed to be engaging, it's supposed to get you excited about math. And I'm certainly excited about math, and if you're watching this, odds are you are too. And if you're not, maybe you watch a few more videos, you'll get excited about math too. So, thanks for watching. I'm going to move on to the senior paper, so we'll get that posted whenever I get that completed. And yeah, keep enjoying math and keep having fun with these contests. See you next time.